Imagine you are trying to perfectly maintain the temperature in a sensitive laboratory or precisely control the speed of a high-performance motor. How do you know if your control system is doing a good job? This is where performance metrics become absolutely essential, guiding you to optimal system behavior. When tuning a proportional integral derivative, or PID, controller, several key performance metrics are used to evaluate its effectiveness. The primary goal is to achieve a stable and responsive system. These metrics quantify how well the controlled variable tracks its desired set point and how efficiently it manages disturbances. The why behind these metrics stems from the fundamental purpose of control: to minimize error. A PID controller adjusts its output based on the present error, the accumulation of past errors, and the predicted future error. Each metric offers a quantitative lens through which we can assess the controller's success in processing these errors. For instance, some metrics prioritize a quick response, while others focus on minimizing oscillation, reflecting different practical needs for various systems. They help you understand the dynamic interaction between your controller and the process it is managing. To practically use these metrics, you would typically run a step response test on your system. This involves introducing a sudden change to the set point and observing how the controlled variable reacts. You then measure characteristics like the rise time, which is how long it takes to go from 10% to 90% of the final value. Another is the overshoot, representing how much the variable temporarily exceeds the set point before settling. The settling time tells you how long it takes for the system to stay within a small error, then around the set point. Finally, the steady-state error indicates any persistent difference between the set point and the actual value after the system has stabilized. By adjusting the PID gain values and observing changes in these metrics, you can systematically improve performance. These performance metrics are not just theoretical constructs. They are critical tools in advanced control strategies. For example, in many industrial applications, specific algorithms like the integral of the absolute error, or IE, or the integral of the squared error, or ISE, are used. These integral criteria mathematically consolidate the error over time, providing a single numerical value that can be directly minimized through optimization algorithms. This moves beyond subjective observation to a quantifiable, objective tuning process, often used in automated tuning software. Ultimately, understanding and applying these performance metrics allows you to fine-tune your PID controller to meet specific system requirements. By systematically analyzing the system's response to changes and disturbances, you can minimize error, enhance stability, and ensure your controlled process operates at its peak efficiency. This leads to reliable and predictable system behavior, a hallmark of effective engineering.